Okay. So we will look at the velocity and acceleration analysis of the four-bar mechanism now. Let's start by drawing the mechanism as usual. Let's say that this is the second pivot. Let's draw this. C is the coupler point, as you might remember. This angle we call beta. This is beta 1, 2. Now you have omega 1, 2 is the angular velocity. This angle is theta 1, 3. Theta 1, 3. And this link 3 is omega 1, 3. So this is link 2, this is link 3, this is link 4. We will assume that counterclockwise directions are always positive for velocities and accelerations as well. So we have the given is omega 1, 2. We want to find omega 1, 3, omega 1, 4, and possibly the velocity of the coupler point, VC. Okay. But we will do the first velocity analysis, then the acceleration analysis. Of course, in order to do the velocity analysis, we should have the position analysis done, which means that we should be knowing theta 1, 2, theta 1, 3, and theta 1, 4. So we'll write the loop equation and take the derivative of that. Loop equation is, A0A plus AB is equal to A0B0 plus AB0B, as you know. I don't want to write that again, but let me write this in terms of complex numbers. E2 A to the I theta 1, 2 plus A3 e to the I theta 1, 3 is equal to A1 plus A4 e to the I theta 1, 4. And there is the conjugate of this, in which we replace E by minus, I by minus I, if you prefer, which is minus. This is the conjugate of it. Yes.
What do you mean by VC?
Huh?
VC.
What do we mean by VC? It is what is the velocity of this point C, the coupler point?
So we won't consider it as omega.
Omega is the velocity of angular velocities are omegas. VC is the actual velocity of a point. Okay, linear velocity. you know, every point inside every link has a velocity, but every link has one single angular velocity. Okay. So we take d by dt of the loop equation, and we get the following. IA2 omega 1 to e to the I theta 1 2 plus IA3 e. The A1 vanishes because it's a constant. IA4 omega 1 4 e to the I theta 1. And the conjugate equation it's quite simple. It's almost the same thing except for I is replaced by minus I. Okay, so we have two equations which can be put into the matrix form actually. Now, the interesting, important point is that this is a linear equation in terms of the unknowns. IA3. I'm just going to collect the unknown terms together, theta 1 3 and theta 1 4 together. So this one will come here. So it will be a minus I A4 e to the I theta 1 4. And then you will have minus IA3 e to the I theta 1 3. And you have a plus because this thing will go to this side. IA4 e to the minus I theta 1 4. This is the coefficient matrix times omega 1 3 and omega 1 4. These are the unknowns equals. This term goes here, so minus IA2 e to the I theta 1 2. And this term goes here, so it is IA2 e to the I minus I theta 1 2 times omega 1 2. Okay. Yes. Omega 1 2 and A2 actually is common in both of these. Well, how do we solve this? One of the ways to do it is the Kramer's rule, if you remember. But it is the determinant. You replace the, for example, if you want to solve for omega 1 3, you replace the column of omega 1 3 with this column. Okay, then take the determinant and divide it to the determinant of the original A matrix. Okay, so let me open a new page and do it here. Omega 1 3 is going to be determinant of minus A2 omega 1 2 So I have replaced, as you see, I have put this thing into here. This is a determinant. And then we have the determinant of the original matrix. Not, it's not a minus, it's just I, A, T, minus. Oh, minus I, and 4. And the same thing, I, A, 4, the minus the determinant. Okay. Well, you multiply these. So you get, for example, A2, A4, and A2, A4 here, and omega 1, 2. So, and then you use the trigonometric identities, I think. But there is something wrong here. I think this is wrong. This has to be a minus. Anything else? Okay. So the multiplication is going to give you the following.
Now, why are you taking determinants of the right side, but you're moving the determinant, when you're moving the matrix from the left side to the right side? Then,
That's the Cramer's rule. Well, you must have learned it in,
yes, but it's on the left side, and W1, omega 1 3 is on the left side. So.
yes,
it's all down.
omega 1, 3 is not on the left side. Just a second. Omega 1, 3 and omega 1, 4 are here. You see?
But you're taking the determinant on the right side, is that of I,
Yes, because that's the Cramer's rule. You in order to solve for one variable, you have to replace the column of that variable with the column of the right-hand side. Okay. Well, I don't know the proof of the Cramer's rule, but you must have learned it in, engineering mathematics, linear algebra, something before. Okay, so we take the determinant here. We take both determinants as a matter of fact, and we get I, A2, A4. They cancel. Well, let me just write this. We get something like this. There might be a sign error. I'm not sure. This is, there are too many, you know. Then you have A3, A4, and kind of the same thing. E to the I theta 1, 3, e to the minus theta 1, 4, minus e to the I theta 1, 4, theta 1, 3. Okay, this, for example, is, this part is e to the I theta 1, 3 minus theta 1, 4. And this is e to the I theta 1, 4 minus theta 1, 3, which is e to the minus I theta 1, 3 minus theta 1, 4, etc. And their additions and so on. You can use the trigonometric identities. There are also some I terms here, which will cancel here, by the way. As a matter of fact, is not A2, but A4 term is going to cancel. And you can use the trigonometric identities and so on in the final results. If you are going to get sine theta 1, 2 minus theta 1, 4 divided by sine theta 1, 4 minus theta 1, 3 times omega 1, 2. Okay, this is the result for the omega 1, 3. That is the velocity of the second link. There is something interesting here, which is this one, sine theta 1, 4 minus theta 1, 3. So what happens if theta 1, 4 equals theta 1, 3? Well, you get a sine of 0, which is 0. So you have a division by 0. Well, in which case the omega 1, 3 is undefined. As a matter of fact, this is a singular position. Why is that? Let's try to understand this physically. This means the following. This means the following position for the 4-bar mechanism. Let's say this is your second link, okay, which is 2. This is theta 1, 2. Then let's say that this is your third link, so that this is theta 1, 3. Okay, and then here you have this whole link is link 2, link 3 rather, and then link 4 extends from here to here and comes to this position. So theta 1, 4 is this one. Do you understand what I mean? The link 3 extends from, let's say, this is A0, this is A, this is B, and this is B0. So it goes A0A, AB, then B0B is the link 4. Okay. So theta 1, 3 and theta 1, 4 is the same angle. They are the same. In this position, the position of the mechanism is singular. You cannot know whether the, with the given omega 1, 2, you cannot determine whether the velocity is going to be in this direction or in that direction, or whatever it's going to be. Okay, omega 1, 3 is indeterminate in this position. just because of the geometry. But of course, you should try to avoid, if possible, such positions in your mechanism. Okay. You know, it's not always possible to have such things, but it can happen. But you can prevent it happening by the design. Okay, so omega-1,3 is solved here. And similarly, we can solve for omega-1,4. Just the same thing. We A2 over A4 this time. Sine theta 1, 2 minus theta 1, 4. 5, 7, 1, 4 minus theta 1, 3. Again, we have a singular position, which is the same position, omega-1, 2. So these are the solutions for the velocities. This is one solution. This is the second solution. Okay. So much for the velocities. Angular velocities. I'm sorry, not the velocities. Then there was one more thing, if you remember. The velocity of point C here. Okay. We want to write the velocity of that point. How do we do that? We write the position vector of point C. Now we have solved for omega-1, 2 and omega-1, 3, remember? So we can solve for velocity of point C. VC as a vector. You can write RC, the position vector, as A2 e to the I theta 1, 2 plus B3 e to the I. I will show this theta 1, 3 plus some theta angle. Okay. So you have this vector A0A. Okay. Then you have this vector, and this is theta 1, 3. This is theta. This distance is A2. This distance is B3. And this is point C. Okay. So we just take the derivative. VC is equal to I A2 omega-1, 2 e to the I theta 1, 2 plus I B3 omega-1, 3 e to the I theta 1, 3 plus well, everything is known here. Okay, so supposing that we have solved for omega-1, 3 before using the loop equations. We know everything, but we might want to express the x and y components. We have to, you know, take the real and imaginary parts of that. So if you want x and y components of VC, you just have to write it e to the I theta 1, 2 in terms of the expansion of cosine and sine, and open it up. Well, I will just write down the result. You can do it yourselves. Minus A2 minus E3 omega 1 3. Okay, so we have found the velocity of point C, as you see. Finding the velocities of specific points is not too hard once you solve for the unknowns in the loop equation. Okay, so much for the velocities for the 4-bar, which is, as you see, is not too hard to do. And if you don't have any questions, I will go on with the accelerations now.
Hojam, excuse me, Hojam.
Yes.
Why is VCX negative? I mean, when you're defining it in terms of X direction.
Well, it's in the negative, you know, we see, for example, if we see is like this X component of velocity, let me just draw it in another color. If this is VC, this X component is negative in the XY coordinate, right?
It's clear now, thanks.
Okay. Okay, the next step is to do the accelerations analysis. Again, what we do is we take the velocity loop equation. VLE is the velocity loop equation, and then obtain the acceleration terms. Our given is here is alpha 1, 2. We need to find, let's say, alpha 1, 3, alpha 1, 4, and possibly acceleration of point C. Okay, that's the A. All right, we need to take the derivative of the velocity loop equation. And by the way, velocity analysis must be done before. Velocity analysis is done. So omega 1, 3 and omega 1, 4 are known. Okay. This is what we assume for a specific position. So let's open a new page and let's write the, well, we just take the derivative of the velocity loop equation, if you remember. So IA2 alpha 1, 2, omega 1, 2 derivative is alpha 1, 2. Minus A2. This is the derivative, omega 1, 2, e to the I theta 1, 2, plus I e 2, 3. Equals So this is the acceleration equation, okay? Well, actually, as we said, the unknowns are two, not just one. But this equation is a complex equation, so it contains not just one equation, but two equations inside it, okay? You can either take the complex conjugate of this, or you can separate it into real and imaginary parts, which will give you two equations. That is, real and imaginary parts will give you equations for the x and y coordinates. Well, because in, you know, in, how can I say, in principle, it is possible, but if you want to do it, you spend a lot of time doing it. Let me try to write down the matrix. There is also the complex conjugate, which I will put here. So let's say IA2 here. I have to erase a few things. Because I'm just, I skipped some steps, so I have to, IA, it should be IA2 equal to 3. Now, this will be theta 1, 4 will go to this side. It will be minus IA4 e to the I theta 1, 4. And plus, yes, this is correct now, is equal to. Huh? Bunu mu diyorsun? Yok. Theta 1, 4. Then we will have, well, yes. This is A4, you are right. Yeah. Then we have a long expression, unfortunately, which A2 this goes to this side, this goes to that side, so this plus A3 omega 1, 2 squared. And one more term, minus A4 4 squared e to the I theta 1, 4. Then we have the conjugate of this, which is A2 omega 1. Plus minus a4 minus 5. So this is the right hand side. Now this is known. Everything is known here. It might be complicated, but it is known. This is known. Okay. You again can use the Kramer's rule, or you can use whatever to solve for this. Eventually, you get the solution. The solution is, you know, it's doable but long. Let me just write you the solution. Actually, it is in your book. You can just copy it from here, but just for the sake of completeness, let me write it. 1 over. Again, the theta 1,4 equals theta 1,3 is a singular position. So there is that. A2 over A3. Four more. Something like this. This is alpha 1,3. You know, it looks terribly long, but once you this is the closed form solution for a 4-bar mechanisms. Once you program it on a computer, you don't have to do anything else. It's just ready for you. Again, the same thing, 1,4 minus theta 1,3. Such is the result. As we know, this is there is a lot of complications. Well, finally, if you want to find a point acceleration of point C, acceleration of point C for some reason, you write acceleration of C is equal to acceleration of A plus acceleration of C relative to A. you know, AA can be found. Once those angular accelerations are known, it's not hard to find these things. I'm not going to go into details of finding this, the accelerations. So, you can find the acceleration at any point once you solve for the angular accelerations. Okay. All right, that's all for the 4-bar. Let's take a break now if you don't have any questions. Do you have any questions? Okay, let's take a break now. Okay. So the inverted slider crank is, as I have drawn before, is something like this. Well, this thing is outside. Inside you have the link going in. So the links are 2, 3, and 4 here. Let's say this is A0, this is B0. Link length is A2. Angle is theta 1, 2. This is A1, the grounded link is A1. And this point, that it contacts is called A, I suppose. Okay, this is an interesting mechanism, especially in terms of the velocity and acceleration analysis, because as we will see, we will get strange terms like the Coriolis term. Anyway, we start from, let me draw the geometry of this thing first. So this is theta 1, this is A1, this is A2, this is S43. Theta 1, 4. Let's call this angle alpha, doesn't matter really. S43 is a variable, as we know. So the loop equation is what? A0A is equal to A0 B0 plus 0A, let's say. So A2 e to the I theta 1, 2 is equal to A1 plus S43 e to the I theta 1, 4. This is the position equation. And simply just looking at the triangle, you can say that S43 squared is equal to, this is the cosine theorem, A1 squared plus A2 squared minus 2A1 A2 cosine theta 1, 2. So S43 can be solved from here, right? Very simply. And also you can use the sine theorem here. Say, for example, A2 over sine alpha, which is A2 over sine pi minus theta 1, 4, because it's the complement of this angle, is equal to S43, which we have found before, divided by sine theta 1, 2. So position analysis is simple here. So the position analysis can be done. And you can find this angle also, whatever you call this angle. Right, so you can find that angle too. Okay, so the position analysis is not a problem here. The velocity, we take the derivative of the loop equation, and we get A2 omega 1 to e to the I theta 1, 2. There's an I here. Is equal to, now A1 goes away, but S43 is a variable, so S43 dot e to the I theta 1, 4 is one equation, plus S43 I S43 omega 1, 4 that's our velocity equation. Now, what is this? What is this supposed to mean? This is velocity of A on link 2, but link 2 and link 3 are connected with a revolute joint, so these velocities are the same. Point A is shared by actually all links, right? Point A is shared by 2, 3, and 4. Velocity of A2 is equal to velocity of A3 because there is a common revolute joint there. For example, if this is omega 1, 2, VA2 will be something like this. Right? But supposedly, actually, I couldn't draw it really well. Let me draw it. It's clear. It has to be perpendicular. Okay, this is VA, and this is perpendicular to VA2. So VA2 is equal to VA3 actually, the same velocity. So this slider does not go in this direction, but it rather goes in that direction, in this direction, in the red direction. The slider's actual velocity is in this direction. Why is that? Because of the following. What is this in the first place? This is the velocity of A point again, but on link 4. VA4. So VA4 is, if let's say this, if this is omega 1, 4, VA4 has to be perpendicular to the fourth link. So let me just draw it in a different color. It has to be perpendicular to this one, as you see. Okay. Maybe I should make it a little bit. So this is 4. And what is this? What is left is, it is the relative velocity of the slider with respect to link 4. Okay, so this is, oh, sorry, velocity of A3 with respect to A4. Okay, this is the relative velocity of the slider with respect to with respect to the rod 4. Okay, and that has to have the direction of well, it has to be along the rod, so it has to be something like this. VA2 has to be this thing. Well, supposedly this and this are parallel. This is VA with respect to A4. And VA4 should not be this long. It should be a little bit shorter, like. So the real velocity triangle, if I draw it again, it has to be like this. This is something like this. It is possible to solve for here for the unknowns. I'm not going to do it. It's relatively straightforward to solve for them. Two equations with two unknowns. Okay, so basically we can solve for, what was it? S for 3 dots and omega 1 4. Just as we have done for the velocities, it can be done. Velocities for 4-bar and slider crank, we can do the same here. There is nothing difficult to do here. Okay, it's just two equations with two unknowns. Let me just write the acceleration equation. D by dt of ULE, well, that's the loop equation, is going to give you the following. equals. That's the acceleration of A3 actually, as we know. We had S43 double that, e to the I theta 1, 4. If we go to the previous equation, we took the derivative of this now. We first take the derivative with respect to S43. And we took the derivative of this with respect to theta 1, 4. We got one term. Now, here, you can take the derivative of this with respect to S43, the second one, okay, which you will get, from which you will get the same thing, S43 dot I omega 1, 4 e to the I theta 1, 4. Plus S43 alpha 1, 4 e to the, there's an I somewhere, I e to the I theta 1, 4, minus e to the I theta 1. Okay, so what are these terms? Let's try to understand them. First of all, this is acceleration of A3 in the tangential direction. This is, this thing including the minus, is acceleration of A3 in the normal direction. So that the total is A3, acceleration of A3 point. Now this point, this is kind of easy to understand. This is acceleration of A3 with respect to A4. Okay. Now these two terms are added up. You will get 2S43 I omega 1, 4, etc., etc. This is the Coriolis term. Okay. And then this is axle.
How is that a double dot or a single dot?
This one.
Not the one, yes.
This one. This is a single dot. This is a single dot. Acceleration of A4 tangential, and this is acceleration of A4 in the normal direction. So that this whole thing is acceleration. These two added up will give me acceleration of A4. So the total equation reads like the following. Acceleration of A3 equals acceleration of A4, which is this term, plus acceleration of A3 with respect to A4, plus the Coriolis term. Okay. This is the Coriolis term, and as you see, the Coriolis term is 2 times S43 dot omega 1 4 I e to the I. Okay. When you have translation with respect to a rotation, you will have this term with respect to rotation will result in the Coriolis acceleration. And physically, as I have said before, it's not very easy to explain because it is physically two different effects combined, and both of these are they come out from different effects. For example, let me show it to you here somewhere. How can I draw it? If you have, let's say, a slider like this, which is inside a rotating rod. Okay. So this is rotating with, let's say, omega, and this is moving with relative velocity of v, let's say, with respect to this. Okay. So the slider is moving with respect to the relative velocity of v. Now the Coriolis term, the Coriolis acceleration, the vectorial expression is 2 v crossed with omega. Was it omega crossed v? I think it was omega crossed v. Doesn't matter for 2 dimensions, but for 3-dimensional motions, omega cross v. This is the Coriolis component. So it has to be perpendicular both to v and omega. So the Coriolis acceleration is some term like this. Acceleration Coriolis is both perpendicular to the relative velocity and the angular velocity of the frame on which this thing is sliding. And the magnitude of it is AC is 2 omega v actually. So as we see here, the magnitude is 2, this is the relative velocity times the angular velocity, and this is the unit vector, which is perpendicular to theta 1,4. So you rotate theta 1,4 90 degrees in order to get the Coriolis term. Again, here in this equation, if we look at it, no, here, sorry. If you look at this equation, what are the unknowns? Alpha 1,4 and S43 double dot are to be solved for. Okay. So this equation, along with its conjugate, gives you 2 equations to solve for the unknowns. But usually these equations are, very, very complete. Well, it is possible to solve them, but it's also possible to make a lot of mistakes here in their solutions. So almost nobody gets them correct in their first trial. The important thing is to understand what is physically going on here. Otherwise, as I said, these equations are very easy to make mistakes on. So we don't expect you to solve them correctly in an exam or something, but we expect you to understand what is going on. During this. Okay, so we have covered more or less the simple mechanisms. There are other four-link mechanisms which we can, model, but they more or less follow the same procedure. I will try to do, well, at least write the equations for one more mechanism, which is a two-loop mechanism, which is called, we have done this before, as you might remember, the quick return mechanism. Let me try to show this. Oh, okay, so the link lengths are, this is A5, let's say. This is A2. This is A4. This is B1 is given. S16 is a S16 is a variable. What else? Let's say this is B0, this is B0, this is A, this is B, this is C, this is B0. B0 is just above A0. So B0 to D0 is on a straight line, and this distance is B0, B1. So A2 is A0, A. A1 is, by the way, there is A1 is A0, B0. Let's see. B1 is 0. S16 is C. And S134 is B0. So there are two loops here. 0A, A0A is equal to A0, B0 downward plus B0. This is actually a simply inverted slider crank mechanism. So let's write it. A2 e to the I theta 1, 2 is equal to minus I, because we are going down, minus I A1 plus S34 e to the I theta 1, 4. This is loop 1. Well, there are multiple ways of doing this. B0B plus BC is equal to, for example, this is one way. B0B plus BC is equal to B0 D0 plus B0 C. Okay, that's the bigger loop, larger loop outside. Or you could use this loop if you like, you know, A0A plus AB plus BC is equal to A0 D0 plus B0 C. That's another possibility. But these two loops, these two equations will be dependent on each other. So it is A4 e to the I theta 1, 5 plus A5 sorry, 1, 5, this is 1, 4. B1 is a constant, IB1 plus S16. So you have two loop equations, as you see. what are the, if you want to write the position equations, the given would be theta 1, 2 would be given. And what we would like to find would be the other variables, theta 1, 4, theta 1, 5, what else? S 3, 4, and S 1, 6. Okay, this we need to find that. We have two equations. Well, we have two vector equations, so which means four equations, which means that they are solvable. We can solve for them. Let's at least do the velocity analysis now. Maybe we have enough time for that. So the derivative of the loop equations are going to give us, for the first one, it will be IA2 omega 1 to e to the I theta 1, 2 equals, derivative of IA1 is 0. So you have S3 for that e to the I theta 1, 4 plus I S3 for omega 1, 4. Yes, that's the velocity. For this is the first loop equation. And the second one will give you IA for omega 1, 4 e to the I theta 1, 4 plus IA5 omega 1, 5 e to the I 5 equals, derivative of IB1 is 0. It is S16 stat. Okay, now these equations, this is true, let's say, given is omega 1, 2. We want to find the following: omega 1, 4, omega 1, 5, S1, this S16 stat, okay, and S3, 4. In principle, it is possible. As a matter of fact, you can solve for it from the first equation. For example, what you can do is solve for omega 1, 4 and S3, 4 dots from 1. Okay. When omega 1, 4 is known, then solve for omega 1, 5 and S16 dots.
When you do this by doing the conjugate,
Excuse me?
we find the conjugate in the.
Yes, you can do either way is okay. Either you can find the conjugate and use it, or you can separate the real and imaginary parts. That's a perfectly acceptable solution as well. Okay. Well, that's the same thing can be done for accelerations, but that's even harder and longer. So I don't want to do it, but it's in principle. You just take the derivative of these equations again to solve for the accelerations. You see the velocities and accelerations are kind of easier because you can write matrix equations for them. The unknowns are linear in terms of the equations are linear in terms of the unknowns. They might be very complicated equations, but the solution is possible. Whereas for the position analysis, it's a little bit harder. So I think I will stop here. The next time I will try to make a general review, hopefully, and try to illustrate these things on some kind of a software, if I can. There is something called neck analysis, which I will try to illustrate some of these results. Although I don't have it here on this computer, I'll try to find a way. We'll see. Maybe I can install it here. Okay, so the next time on Wednesday, as I said, I will dedicate it to making a mostly a review and maybe solving a few more questions. Nothing new. Okay, that's all for today. Let me stop the recording.